A magnitude 7.3 earthquake tore through the seafloor off southern Mexico on Friday, and within an hour its shockwave had crossed a continent, registering on instruments more than 1,000 miles away in the western United States. That distant needle jump isn't the story. The story is what it woke up. This earthquake landed at the exact moment California's faults were measured to be under more stress than at any point in the last 1,000 years. And at the exact moment the San Francisco Bay Area has gone eerily, unnaturally silent. In the next few minutes, you'll understand why an earthquake in another country is being called a warning shot for California, why silence unnerves a seismologist more than shaking does, and why, could this trigger the big one, is a more complicated question than a yes or a no. On Friday morning, the seafloor off the Pacific coast of southern Mexico let go. A magnitude 7.3 earthquake ruptured near the border region of Mexico and Guatemala, along the Middle America Trench, the long subduction zone that runs down the western edge of Mexico and Central America like a seam in the crust of the planet. The first automated reading came in at 7.4. Within minutes, it was revised down to 7.3, once the full seismic record arrived from stations around the globe. That small correction is not an error, and it is not a cover-up. It is simply how large earthquakes are always measured. The first number is a fast estimate built from the earliest waves to arrive at the nearest stations. The final number is the patient, careful measurement built from the complete waveform, once it has crossed the planet and been read by hundreds of instruments. A tenth of a point sounds trivial. On this scale, it is the difference between a rushed guess and a settled fact, and getting it right is the entire job of the global seismic network. For the people living along that stretch of coastline, 7.3 is enormous. The scale seismologists use is not linear. Every whole step up is roughly 32 times more energy released, not double, not triple, 32 times. A magnitude 7.3 does not release a little more energy than a magnitude 6. It releases something on the order of tens of megatons of equivalent explosive force, delivered not in an instant, but in the violent, grinding slip of a fault that had been locked and loading for decades. That energy does not come from anywhere exotic or mysterious. It is the slow, patient strain of two tectonic plates, stored year after year, dumped all at once in a matter of seconds. And yet, as you're about to see, the most important part of this story isn't the shaking in Mexico at all. It's what that shaking reminded a very different coastline it has been quietly, dangerously ignoring. The way this earthquake broke tells you almost everything about where it happened. According to the United States Geological Survey, this was a thrust fault rupture on or near the plate interface, a megathrust style event. Picture two tectonic plates locked together, one sliding beneath the other. Here, the Cocos Plate is diving under the North American plate at a rate of roughly 76 millimeters a year, moving northeast. About the speed your fingernails grow, but carried out across a slab of ocean floor the size of a small sea. In some segments of this same arc, the plates converge even faster, closer to 88 millimeters a year, depending on exactly where along the boundary you measure. That motion is never smooth. The two plates catch, grip, and hold. The strain builds for years, then decades, until the friction finally loses and the overriding plate lurches up and over the descending slab all at once. That lurch is the earthquake. The rock does not stretch like rubber and spring back. It holds and holds and holds, and then it breaks, releasing in seconds what took a lifetime to accumulate. This is the same category of fault responsible for the largest earthquakes on the planet, the great megathrusts of Chile, of Alaska, of Japan. The reason megathrusts sit at the top of the danger scale is simple geometry. The locked contact between two plates is a vast, continuous surface, and when enough of it fails at once, there is almost no ceiling on how much rock can move. Friday's rupture was not one of those monsters. It broke a modest patch of that surface, not the whole seam, but it came from the same machinery, and understanding that machinery is exactly what you need to understand why a quake 1,000 miles from California made seismologists there go quiet and start watching their instruments. Roughly 30 minutes after the main shock, the largest aftershock struck, a magnitude 6.0, still the biggest of the sequence as of the latest data. Behind it came a crowd of smaller shocks, numerous magnitude 5s, including a 5.2 recorded after midnight rolling into Saturday. To someone on that coastline, that cascade feels like the earth refusing to settle. To a seismologist, it looks reassuringly ordinary, and that word matters, so let's be precise. Aftershocks follow patterns that hold up remarkably well across earthquakes everywhere on Earth. The largest aftershock typically lands more than a full magnitude point below the main shock, exactly where this 6.0 sits beneath the 7.3. The shocks arrive fast at first, then thin out over days and weeks in a predictable decay curve. And for every step down in magnitude, you get many more events. A single 6, a handful of 5s, hundreds of smaller tremors gradually tapering into silence. This is the signature of a fault settling into a new equilibrium, not a warning sign of something bigger waiting in the wings. What the data supports going forward is more of the same. 1 or possibly 2 additional magnitude 6 aftershocks in the coming days would be entirely normal, and there is always some outside chance the sequence produces an upper 6 as its largest before it fully fades. The region also registered a pair of small foreshocks before the main event, though in a zone this seismically restless, with 3s and 2s and the occasional 4 rumbling through on almost any given day. Calling something a foreshock is partly a judgment made after the fact, once you already know the big one arrived. That's one of the harder truths in this science. The small quake that turns out to be a foreshock looks identical, in the moment, to the thousands of small quakes that lead to absolutely nothing. There is no reliable tell. You only find out which one it was after the ground has already answered the question for you. The point stands. The Mexican earthquake, taken in isolation, is behaving exactly the way a fault of this size is supposed to behave. Every piece of the sequence, the size of the largest aftershock, the rate of decay, the absence of anything that breaks the expected pattern, reads as textbook normal. Hold on to that, because it's the setup for the twist. A megathrust earthquake under the ocean is precisely the kind that can push water, and this one did trigger a tsunami threat. The Pacific Tsunami Warning Center issued alerts and then, a short time later, stood them down. A wave was produced, but it was minor, roughly half a foot above the normal tide. That's a ripple, not a disaster, and nothing damaging came ashore. It's worth pausing on why the tsunami stayed so small, because it tells you something about the rupture itself. A tsunami isn't caused by shaking, it's caused by the seafloor physically lifting or dropping and shoving the entire column of ocean above it. So wave size depends heavily on how much seabed moves vertically and how much water sits on top of it. A rupture that stays deeper or slips more sideways than up and down, or simply doesn't break a large enough patch of seafloor displaces far less water. Friday's earthquake, for all its energy, did not heave the ocean floor the way a true tsunami-generating giant does. The warning system worked exactly as designed, flagging the danger within minutes because the responsible move is to assume the worst until the water proves otherwise. Then, watching coastal tide gauges in real time and canceling the alert the moment those gauges confirmed the wave was small. That is not a false alarm. That is a safety system doing its job. But the quiet ocean here previews a bigger theme in this story because the most unsettling signal in this picture isn't something that moved. It's something that has gone still. Before this story crosses into California, you need to understand exactly what that stretch of the Middle America Trench is capable of. According to the United States Geological Survey, 7 earthquakes of magnitude 7.0 or larger have struck within 155 miles of Friday's epicenter since 1950. This is not a quiet fault. It is one of the more productive earthquake factories on the planet, and it has a long memory. The largest of those 7 was a magnitude 8.2, which hit the southern extent of this zone in September of 2017. That earthquake was Mexico's largest in a century. It killed 98 people and generated a tsunami. Here's a detail seismologists find genuinely interesting. That 2017 magnitude 8.2 was not the same kind of earthquake as Friday's. It was an intraslab event, a normal faulting rupture that tore deep inside the bending Cocos slab roughly 70 kilometers down, as the plate flexed and cracked under its own descent into the mantle. Friday's earthquake, by contrast, was a thrust on or near the plate interface itself, the contact surface where the two plates are actually locked together. Same trench, 2 completely different ways of failing. One snapped the slab as it bent, like a bar of metal cracking. The other lurched along the seam where the plates grind past each other. The distinction matters because of scale and memory. The 2017 event proves this segment can produce earthquakes. Substantially larger than the one just witnessed, a magnitude 8.2 releases something close to 30 times the energy of a 7.3. So Friday's rupture is not the ceiling here. It is a reminder of a ceiling that sits much higher, and one already reached inside living memory. Now for the thread that ties this entire story together, and it's a real physical thread, not a metaphor. When that magnitude 7.3 ruptured off Mexico, it sent seismic energy racing outward through the body of the planet. Earthquakes radiate several kinds of waves, but the fastest is the P wave, a pulse of compression that moves through solid rock at several miles per second. That P wave traveled the length of the continent. About an hour later, it registered clearly on a seismograph station up in the Yellowstone region of the western United States. Think about what that means. An earthquake off Mexico physically shook the ground beneath the western United States roughly an hour after it happened, and a sensitive instrument wrote it down as a clean, unmistakable arrival. That's not exotic. Large earthquakes are recorded on instruments worldwide every single time, and reading those distant arrivals is exactly how seismologists locate and measure quakes in the first place. but it is the literal, tangible link between two coastlines people usually think of as unrelated. The same class of seismographs that felt the Mexican rupture arrive are the instruments trained day and night on the fault system running beneath California. The Mexico earthquake didn't just make news on the West Coast, it made a mark on the West Coast's needles, drawing a straight physical line from a fault off Mexico to the ground under California. And that arrival is the perfect excuse to ask the question everyone there quietly asked on Friday. Does this mean anything for us? To answer that honestly, you have to understand what California's faults are doing right now, completely independent of anything that happened in Mexico. A study published in the Journal of Geophysical Research, Solid Earth, led by researchers at the University of Bern, working with a United States Geological Survey co-author, reconstructed 1,000 years of stress accumulation across the Southern California fault network. Their finding is the reason for the nervous headlines, and it is stark. Segments of the San Andreas Fault and the neighboring San Jacinto Fault are now locked and loaded to their highest stress levels in the past 1,000 years. Let that land properly, not the highest in a decade, not the highest since the last big one, the highest in a millennium. The study zeroed in on a junction called Cajun Pass and described it as an earthquake gate, a place where a rupture can either stall out or punch through and continue running between the two fault systems. That gate is the hinge of the whole scenario. If it's open when a rupture arrives, a joint failure crossing Cajun Pass could reach roughly magnitude 7.4 to 7.8, and it could strike a far larger area than any single fault event, including the Los Angeles Basin itself, where millions of people live directly on top of the hazard. The single most stressed piece of the entire reconstruction was the San Bernardino segment of the San Jacinto Fault, carrying a load of about 3.6 megapascals, higher than at any point the researchers could trace back 1,000 years, and above its own previous peak from nearly 50 years earlier. A number like 3.6 megapascals means little on its own. But the comparison is the point. This segment isn't just highly stressed. It is carrying more stress than it has at any moment the reconstruction can reach. It is sitting at the top of its own 1,000-year record. And a fault does not care about the calendar. It releases when the accumulated stress finally overcomes the friction holding it shut, whether that tipping point arrives tomorrow, in 10 years, or in 50. That is why seismologists talk in probabilities and never in dates. The physics tells you a fault is loaded. It cannot tell you the hour it lets go. Layer on top of that the southern San Andreas, which last produced a great earthquake in 1857, the Fort Tejon event, around magnitude 7.9. That means this segment has been quietly storing strain for roughly 169 years, longer than the average gap between its major ruptures. The plate boundary keeps moving a few centimeters a year whether the fault slips or not, so every year of silence is another year of strain locked into the rock. This is the real story here. The Mexican earthquake is simply the spotlight that swung around and lit it up. So let's answer the actual question directly, because the internet has already answered it wrong. Can a magnitude 7.3 off Mexico actually load or trigger the San Andreas from more than 1,000 miles away? The honest scientific answer is no, and understanding why is worth a careful minute because it's exactly the point where fear and physics part ways. There are two ways one earthquake can influence a distant fault. The first is static stress transfer. When a fault ruptures, it permanently changes the stress on the faults immediately around it, nudging some closer to failure and relaxing others. This is a genuine, measured effect, but it falls off ferociously fast with distance, mattering within about 1 or 2 fault lengths of the rupture, tens of kilometers, not thousands. At the distance from the Middle America Trench to the San Andreas, static stress transfer is effectively zero. There is no wave of pressure creeping up through Central America into California. No line of falling dominoes. That's simply not how the physics works. The second mechanism is dynamic triggering, the passing shudder of seismic waves themselves as they roll through a distant fault. This one is real and well documented. The 1992 Landers earthquake in California famously set off small quakes hundreds of kilometers away as its waves swept past. But dynamic triggering is weak. It tends to nudge faults already critically stressed and full of fluid, like geothermal and volcanic areas, and typically produces only small events. It can jostle a system already sitting at the very edge. It cannot manufacture a great earthquake that wasn't already coming. So here's the defensible verdict: the Mexican. Earthquake is not a trigger for the San Andreas. It's a stress test of our attention. It arrived at the exact moment California's faults were independently measured to be at their 1,000-year peak, and it's that measurement, not the rupture off Mexico, that should actually hold your focus. Which brings us to the strangest and most unnerving part of the whole picture, and it is not a sound at all. It is a silence. While Southern California's faults sit at record stress, the San Francisco Bay Area has gone unusually conspicuously quiet. Over the past 7 days, only a couple of tiny magnitude 1 tremors registered there. the kind of microquakes you would only ever know about by reading an instrument in a fault system. That is supposed to be constantly creeping and releasing small quakes as a matter of course. That kind of quiet is not comforting. Seismologists have a name for a stretch of an active fault that has gone still while everything around it moves: a seismic gap. And a seismic gap can be the signature of a locked segment silently accumulating strain that will eventually be released all at once. Look at the geography, and it gets more pointed. There is seismic activity to the north of the bay and activity to the south. But in between, there's a gap, a dead zone that halts right around the Santa Cruz Mountain segment of the San Andreas. That is the very same segment that ruptured in the 1989 Loma Prieta earthquake, a magnitude 6.9 that killed dozens, collapsed a freeway, and stopped a World Series. The northern San Andreas above it last broke in the great 1906 San Francisco earthquake, around magnitude 7.9, the disaster that effectively rewrote how the world thinks about earthquakes. On Friday, a small magnitude 3.0 did strike in the Santa Cruz Mountains near Gilroy, sitting right on the plate boundary from which the Hayward and Calaveras faults branch away toward the East Bay. But one small quake does not break a silence like that. And this is the inversion at the heart of today's story. On most of the planet, you watch for the ground to move. On this stretch of the West Coast, the thing to watch is the ground refusing to. The quiet is the warning. So where does this leave us? Off Mexico, the sequence is behaving. Watch for one or possibly two more magnitude 6 aftershocks in the coming days, with a small chance the largest late aftershock climbs into the upper sixes before the sequence fades out. If it stays textbook, it will simply decay away, and that's the most likely outcome by a wide margin. This earthquake was violent, but not anomalous, and not a signal that something larger is imminent along that trench in the near term. In California, nothing about Friday changed the underlying physics. The Mexican rupture did not load the San Andreas, and no chain reaction is rolling up the ring of fire toward Los Angeles. The plates in between are mechanically independent, separated by thousands of kilometers of entirely different plate boundaries. And the roughly 120 to 140 magnitude 6 earthquakes the planet produces every year, about one every 3 days, are the ordinary heartbeat of a restless Earth, not evidence of some new awakening. The globe was never quieter in the past. We simply detect and broadcast more of it now. Look at this year's numbers with a cool head and they confirm it. So far in 2026, the planet has produced 9 earthquakes of magnitude 7 or larger, against a long-term average of about 15 a year, a pace running slightly above normal but nowhere near alarming. The largest of them was a magnitude 7.8 in the Philippines the previous month, and there has been no magnitude 8 anywhere on Earth this year at all. The year is running a touch hot, not off the rails. That distinction is exactly the one that fear tends to erase and data tends to restore. What did not change is the part that actually matters. Southern California's faults are still sitting at their highest stress in 1,000 years. The southern San Andreas is still 169 years into its wait, and the Bay Area is still silent. The single most important thing to watch in the weeks ahead is not another distant earthquake. It's whether that Bay Area quiet breaks with a modest release or keeps accumulating towards something that isn't modest at all. Everything here points to vigilance, not panic. Nothing in this picture is a prediction that the big one arrives next week. What it is a case that the West Coast is closer to the end of its cycle than a comfortable public assumes. The earthquake off Mexico was a reminder, delivered on seismographs, from the eye, Yellowstone Plateau to the California coast, that the ground we stand on keeps its own schedule. The most useful thing it did was make us look. Now the job is to keep looking at the fault that is loudest in the record and at the one that has gone completely unnervingly quiet.